In developing our understanding of quantum wave functions, we've seen that they're inherently complex valued functions. That is to say, for every psi of x, we can also have a complex conjugate psi of x that is got that special relationship where we substitute minus I for plus I, minus I for plus I when we take that complex conjugate. These two functions, by the way, if the function really is complex, they are not equal to one another. So they are different functions. Now I bring all this up because when we do measure physical properties of different molecular systems, what we generally find is that those observables are in fact real quantities. So let me write that down. Observables that we measure are real quantities. Now we also know from the postulates that these real quantities come from operating on some state function, okay, and when they give the result that is an eigenfunction and an eigenvalue of that function, these then are real. So the real question is, does the fact that these are real impose some sort of condition on the operator? Okay, because the eigenvalues are basically a feature of the operator. Now, one thing I want to point out is that if these are real, then they are equal to their complex conjugates. There's no difference between a number and its complex conjugate when it's a real number. Now, what I want to do is take this initial eigenvalue equation and express it as a complex conjugate. So I'll use a different color to distinguish it, but let's suppose we took this and we take the complex conjugate of this operation. And when I do that, I'll end up with complex conjugate of the operator operating on the complex conjugate of the wave function. If I take the complex conjugate to the left-hand side, I've got to do the same on the right-hand side. So when I bring this down, it will be a sub n star psi n star. And these still must be equal to one another. Okay, but we've just noted that the complex conjugate of the eigenvalue must be equal to itself if it's a real number. So I'll have this. All right, where am I going with this? Well, I'm going to now employ a trick that's used often in quantum mechanics to learn something about systems, and that is I'm going to multiply this equation by psi sub n on the left. So when I do that, I'll end up with an equation that looks like this. I'll have psi n alpha a star, the complex conjugate of the operator, operating on the complex conjugate of the wave function, is going to be equal to psi n a n psi n star. Okay, so I've just basically multiplied on the left on this side also. Now what I want to do with this is I want to integrate it, and this is for a single variable function, so I'll make it of x. And I know that this is a constant, so it won't affect the integral, so this will just be a n times the integral of psi n, the eigenfunction of a, times its complex conjugate. And it doesn't matter what order I multiply these things in. If there's no operator in between them, this is just going to give 1 if it's normalized. Okay, so what I have is basically an expression for this that is equal to this this particular eigenvalue. Now I could have done the same thing with my original eigenvalue equation, except now I want to multiply by psi n star on the left-hand side. So I'd have psi n star times the operator operating on psi n, and over on the other hand side I would have psi n star a n psi n. Okay, that's just multiplying this right-hand side by a psi n star. Again, if I want to integrate this from minus infinity to infinity dx, this side over here is just going to be equal to a n times the integral of psi n star psi n dx, and I've just described that that's going to be equal to 1, so this is also equal to an. So I've got that this integral is equal to a sub n, and this integral is equal to a sub n, so these two integrals must be equal to one another. So let's write that out just to make it very plain. So I have this integral times a psi n star a operating on psi n dx must be equal to this integral, fix that, so infinity, minus infinity to infinity, of psi n, not star, but just regular psi n, a star operating on psi n star dx. Okay, so I hope you can appreciate the subtle difference between these two equations. I've got a psi n star with the operation of a on psi n. Here I've got a psi n with the complex conjugate operator operating on psi n star. And so this is the condition that this operator a must satisfy for any arbitrary function that it's operating on in order to generate real eigenvalues. Now it turns out this condition has a name. This is something that describes what we call a Hermitian operator. So any operator that obeys this particular relationship will be a Hermitian operator, and it will have real eigenvalues. All right, so what does that mean for us in a practical sense? Well, it means that since all of the eigenvalues that we actually observe in real life up here are real eigenvalues, that means that observables that we might find in real life are associated with Hermitian quantum operators. So you may recall there was a postulate that said that measurable observables were all associated with a linear quantum operator. Well, now we can add the word Hermitian to describe that. I should mention that Hermitian comes from the name of a French mathematician, Hermite, who did work in this area about 200 years ago. All right, so this is the condition that makes an operator Hermitian or not. Let's see how this works in practice. Okay, we might suspect that since we can measure the momentum, and momentum is equal to minus IH bar d dx, that this must be a Hermitian operator, but can we prove it? Well, let's set up our equation here. So we've got psi star, momentum operator psi, dx, and when we write out what the momentum operator is, we'll have a minus IH bar times psi star d psi dx. All right, now how are we going to make sense out of this kind of expression? Well, what we're going to do is we're going to appeal to an old technique from calculus, and that's called integration by parts. And I'll remind you, I hope that I'm reminding you, that integration by parts means that if I have an integral that could be written as some function u times the differential of a function dv, that I can write that as uv minus the integral of v du. So in other words, we've got to define what u and what v are. That will give us this, and then we invert them somehow in that integral. So in this case, I'm going to let this part be dv and this part be u. All right, the minus IH bar will just be out front no matter what we do. So now when I write this out, I'll have minus IH bar, and I'm going to put a big square bracket around this. U is going to be psi star. dv is just going to be psi. Okay, so this is in effect, this is psi squared. This is the square magnitude of the. We're evaluating this over the range of the limits minus infinity to infinity. And what I want to persuade you is that the square magnitude has the same value at these limits, basically 0, so this term is going to vanish. The other part will now be the integral of v du. So the integration of this v would just give us a psi, and the du will give us a d psi star dx dx. All right, so this is now v, and this is now du. All right, so when we go through and perform this operation, we'll find that our initial integral here is going to be equal to the minus sign here and the minus sign here cancel one another, so we'll have a plus IH bar. We'll have then the integral of minus infinity to infinity psi d psi star dx dx. And so this is going to be the same as the integral, and I'll have psi here. I'll have IH bar ddx operating on psi star dx. But what is this thing here? Well, it is the complex conjugate of the momentum operator. All we have to do is change the sign of I. So in fact, what we've done is we've shown that this is equal to this. So that is in fact exactly the condition that makes this a Hermitian operator. So this verifies for us that momentum is indeed a Hermitian operator, and we can treat its eigenvalues as being real numbers.